If you want to build a kernel and a root file system for a QEMU emulated board where to run interesting binaries of our IoT device, this is the video you were searching for. We will introduce build-root, we will see how to configure it, how to configure the kernel, the libc, the libraries and packages we want in the root file system, how to generate the image, and customize it to be reasonably similar to that of our IoT device, and to have a QEMU-based emulation environment that is debugging friendly and reverse engineering friendly, where to run our IoT executable binaries. Finally, we will execute the generated image in QEMU, and I will show you where to download what's needed to replicate on your PC everything you will see on this video. I am Valerio Di Giampietro. I am an electronic engineer with a background in digital electronics and information technology infrastructures, and I would like to be your friendly Italian hacker neighbor willing to share with you tools and techniques for hardware hacking that I learned by myself hacking many devices. If you have not done yet, please subscribe and click the notification bell below to be notified when new episodes will be released. And now, let's start! This is the 9th episode of the series Hardware Hacking Tutorial. In this complete series, we will talk about the hacking process based on information gathering from our device, building an emulation environment where to run interesting binaries, discovering how the device works, and then hack the device and modify its firmware. This episode is about using build-root inside the Docker container to generate the kernel and root file system for our QEMU emulation environment. Build-root is a very powerful tool, much easier than other solutions. It can be used not only to generate the image for a QEMU emulated environment, but also for a real hardware board, like a Raspberry Pi, a BeagleBone, and many others. As we have seen in the last episode, to build an emulation environment reasonably similar to our sample Gematec router, we have to install build-root version 2015.02, and we have to run it in our Docker container based on Debian Wheezy, because this build-root version will not run on a more recent Linux distribution. We go to the build-root website, click on the download button. We don't want the latest releases because they have newer versions of the libc implementations and of other libraries and packages than the version we need to build a system where to run executable binaries of our sample Gematec router that has a very old kernel, libraries and packages. We move down in the page and click on the release archive, and we get a page with all of the build-root versions released in the last 11 years. We download a tarball with our 2015.02 version. Build-root is not a package that you install with your package manager or a package that you install in /user/local on /opt in your system, but it is a tarball that you typically extract using the tar command in a folder on your home directory as a normal user, because it will do this job inside this directory. It will download, store and compile in this folder the kernel and other configuration files. It will download and compile in this folder every packages needed to run the cross-compilation toolchain. It will download and compile in this folder the libraries and packages needed to build the root file system. It will generate in this folder the kernel and the root file system image. It uses the menu config tool to be configured. This is the same configuration tool used to configure the Linux kernel and many related Linux projects like musilibc, BusyBox, and also some other projects. It has a very good user manual. It is important to note that between versions there are some differences in the commands available. Some commands available in previous versions has been changed in newer versions, so it is always recommended to look at the manual for the version we are using. Luckily, the manual is a part of the Buildroot itself, and the first thing I recommend doing is building the manual using the make manual command inside the Buildroot directory. Our Buildroot version has a 120 pages manual, but a large part of it is dedicated to the developer guide that is needed to modify and add packages to Buildroot. We are only interested in the getting started and the user guide. These sections are only about 40 pages, well written, concise and clear. Buildroot needs some mandatory packages and some optional packages that are listed in the manual. Anyway, our Docker container has already installed all the required packages that we need. We create a folder in our home directory where to store all the files related to this video series. We name this HHT for Hardware Hacking Tutorial. You will find everything on a GitHub repository, link in the description below. Inside this folder, we create a download subfolder where we will store downloaded files. We download here the Buildroot 2015.02 with the wget command. We could also use our browser to download the correct version here. We extract this tar archive under the HHT folder. We create another subfolder, we name it Docker, where to store the script to build our Debian Wheezy based Docker container and the script to execute it. We created this script in the last episode of this series, and you can download them from the link in the description below. We can now split our terminal in two. On the bottom part, we will run the Debian Wheezy based Docker container. On the top terminal, we are on our brand new Ubuntu 20.04. In the bottom screen, we can execute our Docker container creation script. In our case, it completes in less than 1 second because the Docker container is already built, and in this case, there was no need to execute this script again. We can now run the docrun script to launch our container. We are now inside our Docker Wheezy based container, but in the same home directory as in our host machine. We can now run this old Buildroot version inside the Docker container. We enter in the Buildroot 2015.02 folder, and as the first step, we create the manual with the make manual command. It takes few minutes. It generates the HTML and EPUB version of the manual and informs us that it cannot generate the PDF version because it doesn't like the version of some commands needed for this purpose. The HTML version is more than enough for our purpose. We don't have Firefox installed on our Docker container, but we can read the manual with the browser installed on our host machine. The manual has been created in the Output Docs manual folder. I strongly recommend to read the first 40 pages of this manual. To configure Buildroot, we have to configure Buildroot itself to select many building options, including the cross toolchain to use, the target processor and other target options, the kernel version, the libc implementation, what to put in the root file system, and many other options. We have to configure the kernel to select many kernel-related options as devices to support, file systems, etc. We optionally have to configure the libc implementation, typically to include features needed by our IoT device. Optionally, we can configure the init system as a BusyBox. In our case, we will not do this step. We will use the default BusyBox configuration. In case of building the image for a real board, we have to configure the bootloader. In our case, we don't need the bootloader because a QEMU emulated board doesn't need the bootloader. QEMU itself does the bootloader job. One nice feature of Buildroot is that it ships with reasonable defaults for many different boards and or CPU. So usually we don't start from scratch, but select our board if it's available in Buildroot or a similar board with the same CPU architecture. Then we can start customizing the configuration according to our needs. If we execute the command make help, we can get a list of the main targets we can give to the make command. We will see the most important targets later. For now, we can see that there are a lot of built-in configs for many different boards and processors, including a lot of QEMU emulated boards, including our QEMU MIPSEL Malta board. We can execute the make command with our QEMU MIPSEL Malta board as target. This will generate a config file inside the Buildroot folder. Later, we can save this configuration overwriting the configuration shipped with the Buildroot, or we can use a Buildroot feature to store all our configurations outside of the Buildroot tree without overwriting anything shipped with the Buildroot. Once we have set these reasonable defaults for our board, we can start configuring Buildroot itself. Buildroot uses the same menu config configuration system like the one used by the Linux kernel, and the two main commands that we can use to this configuration are make menu config for a text-based configuration, or we can use make xconfig for a much more user-friendly and convenient configuration. We will use this command. We can see that on the left pane we have the options grouped by functionalities. On the top right pane we have the detailed options, sometimes grouped by more detailed functionality. And on the bottom right pane we have the help information describing the meaning of the option we have selected. One very useful command is the edit find command that allows to search an option everywhere in the configuration file. For example, we can see every option where the UBFS string related to the UBFS file system is included as an option name or as an option description. Some options are grayed out because usually they depend on some other options. This help window usually explains what are these other options. The main groups of options are the target-related options as target architecture, binary file format, and some other target-related features. In this case, we have used the configuration shipped with the Buildroot for our MIPS Malta board, and for this reason we have already the correct values and we don't need to change anything. The build options are related to the build process, and they include locations of configuration files and other build options. In our case, we select the Enable Compiler Cache that can speed up compilations, keeping a cache of already compiled items with related compiler options. At any time, we can get rid of this cache removing the .buildroot ccache folder in our home directory. Because we are building an old system, we want to show also options and packages that are obsolete. We select to build packages and libraries with debugging symbols because when we will reverse engineer interesting binaries of our IoT device, we can execute them with GDB, the GNU debugger, and we can put breakpoints at each library function entry, and we can easily inspect parameters passed to these library functions and values returned by them. We select the higher debugging level. We don't want to strip binary files on the target because stripping means removing debugging information. We disable GCC optimization because GCC optimization is an obstacle to reverse engineering and debugging executable binaries. Optimization can make harder to understand the flow inside our library functions. The toolchain options are related to the toolchain configuration. Buildroot can build its toolchain, recompiling everything from source, including the GCC compiler and the binutils, or can use an external toolchain. Using is toolchain is a quite common choice, and it is our choice. We use a very old kernel, so we manually specify the version to select the kernel header files that will be used to compile many tools in our emulated device. The kernel is always backward compatible, but can introduce new features in new kernel versions. The exact kernel version is not so important for the header files, but it is important to not select header files that have a newer version than the kernel that we will install on our device. This is to not risk that some binary in our device will use newer kernel features not available on our older kernel version. Using older kernel headers is usually okay. Anyway, we will manually select the same kernel series that we have on our sample Gematec router. We enter as Linux version the version of the kernel we have to build. It is the same version as the kernel we have on our sample Gematec router. As C library, we use musylibc, that is the same C library used in our sample Gematec router. We select the same musylibc version needed in our sample router. For now, we leave the musylibc configuration file inside the buildroot tree. Later, we will see how to store all of our configuration files outside of the buildroot tree. We enable large file support, IPv6, RPC, and YDHR support as it is in our sample Gematec router. We enable Linux threads and thread library debugging. We build the cross GDB for the host. This is the GNU debugger to run on the host. In the target, we will run the GDB server that is a minimal debugger that can be remotely controlled by the GNU debugger running on the host. We enable also the text user interface, a sort of GUI interface on the terminal, and also Python support. We select the latest GDB version available. It is important to note that sometimes modifying some options can produce some compiling errors that can be more or less difficult to fix. For this reason, it is better to modify only the options we need. The system configuration options are related to our target, and it includes the hostname and banners. We leave the default here. We select MD5 as password encoding. It is not important, but just to have the same encoding as in our sample device. As init system, we select BusyBox as in our sample device. As /dev management, we have three options. Static, that means that the device directory is statically populated when we build the root file system image and will not dynamically change adding or removing a new device in the system. Dynamic means that /dev will be mounted on a temporary file system and dynamically populated based on the device attached or removed from the system. We have two possibilities, one with devtmps, having the kernel populating the /dev directory, the other with mdev. We select devtmps that it is the more traditional dynamic way of populating /dev. We accept the default for using BusyBox as the default shell, to have a login prompt after boot, and we select to install timezone-info as in our sample device. Later we will select a post-installation script For now, we leave this option empty. The kernel options are for Linux kernel-related options. We can select the kernel version to the same version as in our sample device. We accept the default VM Linux for our kernel binary format. It is a format accepted by QEMU. The target packages options are a very huge list of packages and libraries that we want in our target root file system. We will not go in much detail here. Anyway, we have to select some compression tools that we need as libzip2 and xzutils. We want BAT, GDB and GDB server on the target device to help us in the reverse engineering job of the binaries we are interested in. For the same reason, we also want strace. We want also some development tools to simplify our job in the target device. In the file system and flash utilities, we want to enable the file system tools and flash utilities that are installed on our sample device and that we want to emulate in our QEMU board. In the libraries section, we want the libraries used by the sample device binaries we are interested in. For this reason, we select libsha1, libssh2, OpenSSL, expact and JSON-C. In the network application section, we select some tools needed to transfer files between the emulated machine and the external world as rsync and ncftp. We select some other tools that we need in the shell and utilities and in the system tools section. In the file system image section, we select the format of our root file system image. This is the format that will be used by QEMU. We will use the default that is an ext2, a compressed file system image. Buildroot allows also to generate a bootloader for our device, but in our case we don't need the bootloader for QEMU because QEMU can do the job of the bootloader by itself. In the host utilities section, we select the utilities related to flash EEPROM file system we have in our device. These are utilities that are built to run on our Linux system and not on the target device. When satisfied with our configuration, we save it. It will be saved in a .config working file inside the buildroot folder. If we want to permanently save this configuration, we can use the make save defconfig command that would save the configuration over the defconfig files shipped with the buildroot that we have used to do the initial configuration for our QEMU emulated board. In this way, we are overriding a file shipped with the buildroot and located inside the buildroot folder. Later, we will see how to store our configuration in an external tree outside of the buildroot tree. Configuring buildroot is not enough. We have also to configure the kernel and the MUSI libc library. To configure the Linux kernel, in general, we could use a similar GUI interface to the one used to configure buildroot with the command make linux xconfig. But our Linux kernel is so old that for this type of configuration it requires the very old Qt version 3 libraries that are not available on our old Debian Wizzy, and it doesn't like the Qt3 compatibility layer that is installed on our Debian Wizzy. This means that we have to configure the kernel the old way using the text-based user interface. Without going into much detail, in the kernel we have to configure the preemption model to be a preemptible kernel as in our sample device. We have to include the NAND device support for the NAND flash simulator needed to simulate the UBFS file system and the UB device support. In the file system section, we have to enable support for JFFS2, UBFS and SquashFS file systems because some of this file system are used in our device. When we click Save, this configuration will be saved in a .config working file inside the kernel sources. We will see later how to save this configuration outside of the build.root folder. We also need to configure the muslibc library for mainly two reasons. We want to compile the muslibc with debugging information. This is very important because we want to run the IoT executable binaries we are interested in with GDB, the GNU debugger, and we want to put breakpoints on library function entry to see parameters passed and values returned. We need to include features used in our sample device. We discover these features with a trial and error approach. Initially, we compile the muslibc with the default options. Then, when we receive errors launching our IoT executable binaries, we investigate these errors and we find that these binaries require some options to be enabled in our muslibc library. The muslibc library is very old and doesn't support the graphical user configuration, so again, we have to use the text-based configuration with the command make muslibc -config. Apparently, we could enable the debugging option in compiling this library, but for unknown reasons, if we enable this option, the compilation fails with compilation errors that I wasn't able to fix. This happens because when the debugging option is enabled, on some sources there are some conditional directive statements that include some broken code. So we are forced to use a trick, adding debugging-related compilation option to GCC under the compiler warning section that was originally intended to add compiler option to increase or decrease warning verbosity. We add the options -w_all that enables all compilers warning messages. -g_gdb produces debugging information to use with GDB. -g3 to include extra debugging information like macro expansion. When we click Save, the configuration is saved inside the muslibc source folder. We can see soon how to save these configurations outside of the build.root folder. We are now ready to type make to build everything, to build the toolchain used to compile the kernel and everything that goes in our root file system, to build the kernel, the muslibc library and all other libraries and packages we have selected, to create the root file system image that will be used by QEMU. Unfortunately, typing make now, we will receive compiler errors when compiling some packages. The error says that we are not using the -fpic option in compiling some shared object. PIC stands for Position Independent Code, and it is a switch that should be used when compiling shared objects like library functions, because when a shared object is loaded in the process address space, it could be possible that the address desired by the shared object is already occupied. For this reason, it must be possible to relocate the shared object to a different address. This can be done only if the shared object uses relative addresses for jumps and memory references. This means that we have errors in the compilation options of the related packages. It is possible that these errors have surfaced because we have disabled compiler optimization to facilitate our debugging and reverse engineering job. It is possible that with compiler optimizations enabled, the generated code would have been more compact and would have used relative jumps and relative memory references anyway for optimization reasons, without the need for the -fpic option. This could be the reason why these compilation switch errors have been undetected in the build root configuration of these packages. To fix these errors, we have two possibilities. Globally add the option Enable Shared in the build root toolchain additional GCC option. In this way, everything will be compiled with position-independent code. Or we can patch build root for the impacted packages in the build root tree. We will follow this route. Build root allows us to keep all of our customization in an external tree outside of the main build root folder. This is important to keep our customization separate from the build root application and to be able to manage it in a revision control system like Git. To do so, we can create a parallel external tree where to keep our customization as the tree is shown on the screen that follows build root recommendation. board/mips4kc is our fictitious QEMU board. We store the kernel configuration here. Everything inside the overlay folder will be copied on our final image just before building the image. This allows us to add or overwrite anything we want. In this case, we add the script to customize our shell prompt. Here we have the postbuild.sh script that will be executed just before building the image. This allows us to modify some files or to dynamically add files and folder to the image. I will use this possibility to copy the root and firmware files of our sample device inside the root image of the emulated board. The files config.in, external.desk and external.mk are needed by build root. They will be especially useful to add custom packages, but this is not our case. Under configs, we put the build root configuration. It is the customized version of build root defconfig for our QEMU MIPS Malta board. On the same directory, we put also the musylibc configuration. Under patches, we could put custom patches. In this case, we don't have a packages folder because we don't have custom packages. To have build root using our external tree, we have to invoke the make command, passing it the br2 underscore external variable as is shown on the screen. Executing make help in this way, we can see that our defconfig file is available to be used to customize the configuration. If we do additional customization, we can save the new build root configuration with the command make save defconfig. One interesting aspect of this command is that it saves on our file only the configurations that have a different value than the default. This largely simplifies reusing the same configuration in subsequent build root versions that can have many additional options. Once the br2 underscore external variable is passed to build root, it will save its value inside the configuration file in the output directory, so we can omit this variable in a subsequent invocation. To save the Linux kernel configuration, we have to use the command make linux update defconfig. This will save the kernel configuration, again stripping the default values to the file specified in the build root configuration file, that in our case is the one shown on screen. To save the musylibc configuration, we can use the make musylibc update defconfig, but we have to put the file name where to store the configuration in an environment variable. This is not very convenient. To simplify our job, we can write a wrapper script to launch the build root make command as the one shown on the screen, where it will run only inside the Docker container to not mess up the compilation process, because if we launch this command inside our Linux host, it will run and maybe will compile something before giving compilation errors, but we don't want to have some object compiled with a different ZCC version like the one on our host Linux. We want to compile everything inside the Docker container. If we use the save defconfig option, we will execute make with the correct environment variable to be sure that the configuration files are saved where we expect. Same thing if we use the musilibc update defconfig to save the musilibc configuration. Otherwise, we execute the make command explicitly setting the br2_external environment variable, logging the output on the terminal and on a log file. Summarizing what we have seen till now, we will have the following layout on our project directory. The BR folder. Inside we have the patch files to fix the missing -fpic GCC option on some package files, another patch file to fix the download URL of another package file that has changed since when this build-root version was released, the BR patch script that we will use to patch our build-root, the ext3 seen above, where our build-root configuration and customization is stored, the Docker folder with the scripts to build and run the Debian Wheezy Docker container, the download folder where we have downloaded the build-root gzip tar file, the QR folder where we have the script to start QEMU. This script includes the path to the kernel and root file system image generated by build-root. If we change something in build-root and will recreate the kernel and root file system, the QEMU wrapper script automatically will pick up the latest built image. Finally, the build-root 2015.2 is where build-root is. We can now restart from scratch building our image. We can clone the GitHub repository where I stored this project. You will find the link in the description below. We enter in the cloned directory, we enter in the download directory, we download the build-root tarball, we extract build-root in the parent directory, we enter in our BR directory where we have our custom build-root environment. We patch build-root with our BR patch shell script. We then enter in the Docker directory. We build our Debian Wheezy based Docker container, but it is already built, so the build script terminates immediately. We enter in our custom build-root directory and do the build-root configuration. This configuration set also the configuration files for the kernel and the musilibc library that are stored in our external tree. We can now execute the make command with our brmake wrapper script, and our toolchain, kernel and root file system will start building. Depending on our internet connection speed and on our Linux machine speed, it can take 1 hour or many hours to complete the building process. Once everything has been built, we can exit from our Docker container. We can start our QEMU emulation. In the next episode, we will use this emulation environment to reverse engineer some of our sample device executable binaries we are interested in. If you have found this video interesting, please subscribe, help this channel grow, share this video with friends interested in hardware hacking. Please click the subscribe button below and the notification bell to be notified when new episodes will be released. And don't forget to click the thumbs up icon. Please give me feedback and don't hesitate to ask me questions, writing comments below. Let me know if you have suggestions to improve this channel or if you have enjoyed or not this video. Every comment, but positive and negative, is welcome. Thank you for watching. See you again on this channel.